And our second speaker of today is Peng Shan from Tsinghua University. And she will talk about cyclotomic level maps and associated varieties of simple affine vertex algebra. So let us welcome our speaker.
Thank you very much. I'd like to thank the organizers for giving me the opportunity to give a talk. What I'm going to talk about today is a joint work with Wenbin Yan and Qixian Zhao, who are both in the audience. And here are their photos. I leave it to you to find them. So the paper, we just put it on the archive this week. And as you see, there are two parts in the title. There's cyclotomic level maps and associated varieties of simple affine vertex algebras. Actually, we study a map, which is the cyclotomic level map, and the reason we studied it was motivated by willing to understand associated variety of simple affine vertex algebras. So I will first explain you the result we obtained on these maps, and then I will explain you a conjecture on this associated varieties. Okay, so we start with a simple Lie algebra over complex numbers, and I will denote by capital G the connected reductive group corresponding to it. And then N is the nilpotent cone in the Lie algebra, and it has the adjoint action of G on it. And then I denote by N underline the set of nilpotent orbits. And so there's a partial order on this set given by O1 is smaller than O2 if it is contained in the closure of O2. And then there's a classification for orbits in all type, and this is so-called Bella-Carter classification. So it says every orbit can be written as what is called saturation of a distinguished orbit in a Levy. So here, distinguished means a nilpotent element which is not contained in a proper Levy. There's some equivalent definitions by saying centralizer is unipotent. And then, so for each orbit, you can find a Levy subgroup and a distinguished nilpotent orbit for this Levy, such that your orbit at the beginning is the saturation of this distinguished orbit, meaning that it's the set obtained by letting the G group acting on OL. Okay, and then the definition of this cyclotomic level map is quite, it's not hard to explain. So you write your orbit as the saturation, as I said, and then you take a nilpotent element in this distinguished orbit OL. And then by Jacobson-Morozov theorem, you can find an SL2 triple EHF in this Levy, and H is the semi-simple element. So if you consider the adjoint action of H on the Lie algebra of L, it gives a weight decomposition where Li is just the elements where H bracket X times I is equal to Ix. And so you get some integers here. And then these are the weights for this SO2 action. And then so you take 2A to be the maximal value of I, such that this weight space is not 0. Okay, and turn out this must be an even positive number. So that's why I denoted by 2A. And then the definition of this map is just it sends this orbit to A plus 1. Okay, and it's a fact that the image of this map will lens between 1 and Coxeter number, because alpha, if you take the highest root and take the regular weight, it gives Coxeter number, so you cannot get anything bigger than that. Okay, and then we prove some results. Like the reason why we look at this map, I will explain it later. But we prove something, some property of this map. So the first one is the most important one, is that for any integer which belongs to the image of this map, then there are several of them, but you can show there exists a unique maximal orbit in the image of actually all the elements smaller than m. Okay, so this gives you a way to assign a nilpotent orbit to any integer which belongs to the image of this map. And further, if one's orbit is smaller than the other, its value under this level map is also smaller. And if an integer is smaller than the other, and they both belong to the image, then this orbit we assign to it, this O of m we assign to it, will satisfy this partial order relation. So O of m1 will be smaller than O of m2. And then you can also show that the closure of an OM is just the unions of all the orbits whose value is under this map is smaller than n. Okay. So the proof of this theorem is a case-by-case computation. There's a classification of nilpotent orbits, and then you can classify, you can compute them, and it's very explicit. So, but there might the statement seems very geometric, so there might be some better proofs. But for now, this is the proof we come up with. But just give you some idea of how it looks like. In type A, you know your nilpotent orbit is indexed by the Jordan type of your nilpotent elements. And so it's given by a partition of n. So here I denote Q is Q1 bigger than Q2, etc. And then the value of this orbit under the cyclotomic map is just the Q1. It's the largest number in the partition. And then, so you can get all the numbers from 1 to n because you can get any partition whose first row is some number between 1 and n. And then if you pick any of them, this biggest orbit we assign to them is OM. It's just the partition with as most parts of m as possible. So you write n equals to m times some number plus v, which is smaller than m, and then this is the partition you obtain in this case. And then if you read the paper, there is a table for the exception types. And then, for example, I copied here the case for E6. I have to separate it into two parts. And then, so the top part is the Balacarter label of the orbit. And then the number here on the second row is their image under the cyclotomic map. And those numbers between the square bracket is the orbit corresponding to this number. Okay, so you can read from this that, for example, in E6, the image of this map will be 12, 9, 8, 6, and all the numbers below 6. Oh, the colors. The dark blue means. The dark blue means it's an even orbit, and the light blue means it's a special orbit which is not even, and the white means it's not special. And if it has a red, I don't know if it can be seen well, but if it has a red boundary, it means its dual orbit is even. Okay, I also put the diagram for G2 for fun. Okay. In G2, you get 6, 3, 2, 1. Okay. So then we want to relate this map to another map, which is defined on the conjugacy classes of Weyl groups. So you have, let W be the Weyl group of G. This is the normalizer of a maximal torus quotient by the torus. And then I will denote by W underlying the conjugacy classes in this group. Then you can define a map in the following manner. You know that W acts on the Lie algebra of the torus, which is it is a finite reflection group. So this representation is defined over Q. So you can consider the characteristic polynomial of an element in W. So W is finite. So this eigenvalues are all roots of unity, and so this characteristic polynomial decomposes as a product of cyclotomic polynomials, and I write them as phi m1 to phi ms. and here M1 is bigger than M2, and etc. And then I just define the image of this conjugacy class to be M1, to be the biggest integer which appears for the cyclotomic polynomial. And I also guess this is the reason we call it cyclotomic level map. So the characteristic polynomial is invariant under conjugation. This is well defined. Right, and then we want to relate the two maps we just defined. So we want to relate them through some maps Lustig have defined. So Lustig constructed a surjective map from conjugacy classes of W to conjugacy classes in the nilpotent cone in the following way. So you pick a conjugacy class, and then you look at elements of minimal length in this conjugacy class. And he proved there's a unique unipotent orbit in G, which among these minimal there's okay, you consider all the unipotent orbits intersecting this BWB for W's minimal length, and there's a unique unipotent orbit, unique minimal unipotent orbit among them. And so then you just, this is orbit you associate to this conjugacy class. And then he also constructed a canonical section of this map, which is starting from an orbit here. You look at its pre-image under this map, and you take, in some sense, the most elliptic element in this fiber. That is an element whose fixed points in the torus, in the carton, has the minimal dimension. Okay, so there's some other way to look at these maps using loop groups. This is what we will use today, and so so I think some part of this map already appeared in work by Kashtan Lustig on the loop groups when they study fixed manifolds in flat variety, and then Zhi Wei Yun gives the precise relation with Lustig's maps I introduced before. So we consider a loop group for G. So LG is G. You take the C points of this loop group is the C double parenthesis T points of the group G, and then you have some positive loops L plus G, which is corresponds to you take points in this C of with like a formal power series. And then you have their Lie algebras, which I denote by LG and L plus G. And in this loop Lie algebra, you consider a part which there's a little heart here, means that these are topologically nilpotent elements. This means in the t-adic topology, it converges to 0. And generically regular semi-simple elements. So if you base change to the algebra closure of this field, then you get some regular semi-simple elements. So so this this is an important locus where many people study. And then for an element here, we can talk about its type. So for an element here, it's regular semi-simple, so you can look at its centralizer in the loop group. This is a maximal torus in the loop group. And then Kashtan Lustig showed the LG conjugacy classes of maximal torus in LG is in bijection with the conjugacy class of Lie group. So we say gamma is of type this W if its centralizer corresponds to this conjugacy class under this map. And then one can also consider a so-called root evaluation map. This is a map defined on the set of roots of G and takes values in rational numbers. So you just pick a root, and then up to taking some extension, you can conjugate gamma to a fixed torus. So you can fix what corresponding to the definition of the root system. And then you take the value of alpha on this point and look at its valuation. It gives some rational number. So this is how it's defined. And then so you look at all the elements of type W and look at their valuations, and somehow there's some minimal root valuation among them. So an element gamma is called shallow if its root valuation is minimal. Okay, and then so we can define reduction types for elements in this topological nilpotent regular semisimple part. The definition is the following. So you look at the affine Grassmannian, which is the loop group quotient by the maximal compact subgroup. And then inside it, you can consider an analog of Springer fiber, which I denote by Grassmannian sub gamma. This is you take all the cosets here such that the adjoint action of G inverse on gamma gives you applied to gamma gives you an element in L plus G. Okay, and so L plus G is this thing. So here you can evaluate T to 0. Okay, so so when you have an element here, you evaluate T to 0, you get an element in the finite G. And this thing is only well defined up to G conjugacy because here you have an ambiguity of choosing an element in the conjugacy class. And so this provides you a map from this set to the nilpotent orbits in the nilpotent cone. And we say the reduction type of an element gamma is just all the orbits such that the fiber of this map is non-empty. Okay? So all the orbits can be realized as reduction of some elements of this form. And then we take RT min to be the minimal elements in this set of orbits. Okay? There can be several of them. And what Zhi Weiyun proved is that for any W, for any conjugacy class, you consider all the shallow elements of this type W, then there is a unique nilpotent orbit which belongs to the minimal reduction of all elements of this, all shallow elements of this type. Okay? And so this allows you to assign an orbit to a conjugacy class in the vowel group, and this is called the minimal reduction type map. And he proved that this is the same map as George Lusick constructed. And then there's also a section for this map. This was already constructed by Carson Lusick, which is you start from the nilpotent orbit, and then you can take what is called a generic lift of it. It's like in the set E plus T times L plus G, you have an open part where elements are all of type W, and so you take an element there. So Zhi Wei also showed that this Carson-Lusick map matches the section psi before. Okay, and our second result is a compatibility of the map I defined at the beginning with these maps. So you remember at the beginning I explained you a map from nilpotent orbits to integers, and also a map from the conjugacy classes of vowel group, and this map factorized through this minimal reduction map. So this is a surjection map, and so this means this is constant on the fiber of this map, and so it also commutes with the Carson-Lusick map. Okay, any questions? Okay, and the third thing we want to relate it to is so-called two-sided cells. So as I said, we'll tell you all the results we have, and then I'll tell you the connections between these results. So to talk about two-sided cells, we consider the affine Lie algebra. This is a central extension of the loop algebra. And then I fix a finite carton, and then the carton here, H hat is that plus the central element, and take its dual. It contains the zeroth fundamental weight. And then I let W affine denotes the affine vowel group. And G check will be the long length dual of G. And then N check is the nilpotent elements in G check. And then Lusick showed there is a bijection between two-sided cells in the affine vowel group and conjugacy classes in this n-check, in the nilpotent orbits in n-check. Okay. And so now so now you can consider the following. So for any m, okay, so maybe I will go to the second page. So what we did so far, now I put it on the g-check side. Okay, so what I did is for any m, an integer between 1 and the cosinus number of g-check, which is h-check, defines an orbit o-check. No, not for any number. For any number in the image, I have an orbit. And then if a number is not in the image, I just take the largest number in the image, which is below it. And I assign an orbit to any integer between 1 and h-check in this way. And on the affine algebra side, I take this integer m, and then I consider the weight, which is m times the zeroth fundamental weight plus rho. Rho is the half sum of all the positive roots. And then, so this is an affine weight. You take a unique dominant translate of it under the affine Weyl group. This is denoted by psi m. Okay. So when m is in this region, this weight is singular, so it has a stabilizer. Well, usually has a stabilizer, which I denote by Wm. And this is a finite group. This is a finite Coxeter group, and I take small Wm to be the longest element in this group. And the third thing we prove is that assume G is simply laced, then there is for any m under Lustig's bijection, the two-sided cell of this particular element is the two-sided cell corresponding to the nilpotent orbit, defined in this way. Okay, so the simply laced assumption may not be necessary, it's because we only proved it in this case for now. And so yeah, maybe one needs some modification of the statement in non-simply, which is simply not yet thought about the non-simply case. So okay, any questions? If not, I will move to associative varieties of affine vertex algebras. So I think we had a nice introduction by Tomoyuki yesterday already. So, but we'll consider a very particular class. So you take a level which is, so I still work with this affine algebra G hat I had before, and I fix the level to be m minus h check. This means if I consider a weight at level kappa, then its rho hat, this affine rho hat shift is m lambda 0 plus rho. This was, just reminds you, this was the way I was looking here. Okay. And then, so yeah, you assume n belongs to this region, then this is, apart from the case kappa equals to 0, which is an easy case, the other case is called non-admissible levels. And then I take L kappa to be the simple quotient of the universal affine vertex algebra, which is, as a module, is given by this induced module. And then, as we heard from Tomoyuki's talk yesterday, that for any vertex algebra, you can associate associative variety. And in the case of the universal affine vertex algebra, this associative variety is just a G star as a Poisson variety. And then we'll use the Killing form to identify it with G. And then this is a quotient. So LK is a quotient, so it's an associative variety. It's a subvariety. It's a closed subvariety in G star. It is Poisson and it's conical and it's stable under G action. Okay. And then one more definition. So an important class of vertex algebra is so-called quasi-Lie vertex algebras. This notion was introduced by Arakawa in the Kawasetsu. And so the definition is that if the associative variety of vertex algebra, so it is Poisson variety, if it has only finitely many symplectic leaves, then you say it's quasi-Lie. So in the case of this simple vertex algebra, you can observe that it is quasi-Lie if and only if it is contained in your potent cone. Because otherwise have some continuous part in the semi-simple part, so it cannot be finite. Okay, Okay, and to explain the conjecture, basically, I need to tell you. Okay, so this is a glance at the conjecture. So you start from the simple vertex algebra and want to describe you what is its associative variety should be. So I need to. So what you have at the beginning is just G and the number M. So from a number M, I need to output some orbits and some sheets from it. So this is explained on this page. So you start from this number M, and by what is explained, we attached a nilpotent orbit in the dual nilpotent cone. And then we write this orbit as saturation of some distinguished orbit in the Levy. So this Levy is denoted by L check. And then we use some duality map, which is well known in representation theory, which is defined by Babbage, Vogel, Lustig, and Spatishton. So it produces you. So you take from the orbit here, it produces you some nilpotent orbit in the Longlands dual the algebra. So this is one ingredient, and another ingredient is that. So here you have a Levy L check, and I consider it's Longlands dual L, and I take a parabolic subgroup of G whose Levy is this L, and then okay, its radicals denoted by U, and these are their Lie algebras. So I denote by the ZL, the center of L. Then the sheet associated to L and the nilpotent orbit in L is just given as follows. So you consider this map of G acting on P, the Lie algebra of P, and you do the diagonal quotient by the group, and it maps to the Lie algebra just by action. And then you take the image of you should take the image of G cross P of this part in the Lie algebra of the parabolic. Like you take the center of L, you take your orbit in the Levy, you take the radical part, and then you induce it, and then take its image. And then this gives this gives you a sheet. And then so if we start from M, you first get this, and then you get this distinguished orbit. You apply the duality, you get the orbit in the Lie algebra, and you consider its sheet. This is the output. And then the conjecture is for G simply lays and M an integer in this region. So kappa is as before M minus H check. Then the associative variety should be the output of this M by the procedure I explained. Okay. There is some reason. I'm not sure I'll explain today. So yeah, maybe I'll just say my following sentence. So this conjecture is explained by some 4D mirror symmetry, which Wenbin probably will talk about it next week. And this is started from some physics idea in 4D n equals to 2 theory, and then we sort of try to understand in terms of Lie theory. And the idea is that if you consider, so vertex algebra, you consider representation of this vertex algebra for affine Lie algebra. Then on the other side, you should consider some Hitchin system for the Longlands dual of this affine Lie algebra. And this is also the reason that I'm not doing non-simply laced type, because for those, I will need to consider twisted affine Springer fibers, and I believe most of this can be done, but this haven't been carried out yet. So so for simply laced, it's easier, and so from that prediction and trying to make some analog of Springer theory in the affine case, and also based on some work of Arakawa, Futoni, and Crick, we came up with this conjecture. But I want to point out, so although initially there are some inspirations from this 4D mirror symmetry, but actually this kind of statement was not predicted by physicists. So this is not something reformulation of what physicists have predicted. So This may give you a reason not to believe it or not. I don't know. It depends on your point of view. But for me, it's nice because it's a uniform description for the associative variety. Yeah, and as I said, there should be a version for all the G. And moreover, there's an important corollary of this is that this gives you a way to detect when for which kappa your L kappa is quasi-Lees. Because if you have a non-trivial Lévy, then with a non-trivial center, then if you have a Lévy which is not torus and has a non-trivial center, then this sheet will never be contained in the nilpotent cone. So this happens only if your original orbit is already distinguished. So this and this can be computed for all the m. So for all the m, you can just read the list in the paper and see which one is distinguished, and this gives you a list of values where at least conjecturally this LK is quasi-Lees. Yeah. No, this not. I mean, so first of all, for all the physics, what am I aware of? You consider Hitchin system. Well, there's some relationship with Springer fiber, but you consider the cases where there's a C star action. So m has to be some regular number. In this case, for other m's, it doesn't happen. And also, what appears in those cases, it's conjectured to be quasi-Lees. So it doesn't see the sheet part in this statement. Okay, and this are some evidence where this conjecture has been proven. So maybe I will not go through the list here. If you're interested, you can read the paper and see the corresponding cases. I just want to say that that the reference here, GK stands for Gorelick Katz, and JS is Jiang and Song, and AM is Arakawa Moreau. AFK is Arakawa Futoni and Kriska. So these people have did many nice work on computing the associative varieties of simple VOAs, and then these are the results they obtained. And so far, all the cases where this variety has been computed, it's conform with our conjecture. Okay, and then I want to explain. I have something like 15 minutes, 20 minutes. Okay. So I want to explain some relationship with affine Springer theory. So let's revisit this BVLS duality map, how it is defined. So it is defined in the following way. So you start with a nilpotent orbit in a dual Longlands dually algebra, and then you pick an element in this orbit, and you have a SL2 triple EH and F. And then you can conjugate it such that this semi-simple element is dominant with the choice of dominant chamber given at the beginning. And then so I take lambda to be half of this semi-simple element, and this, since it's an element in the dual the carton of the Longlands dual, so it naturally identifies with the dual space of the carton of the initial G. So this is a weight for G, and it gives you an infinitesimal character for G, the infinitesimal central character for G. And then turns out among all the primitive ideals, so I'm going a bit wild now. So I think I try to make it accessible to students at the beginning, but now I just allow myself to talk about some terms, maybe, yeah, maybe this is for the global picture part. So yeah, but primitive ideal is possible to explain. So you take simple modules and to take its annihilator, and it's in the enveloping algebra. These are primitive ideals. So given the infinite character lambda, you have several primitive ideals attached to it of this central character, but there's a unique maximum one among them, and this is denoted by J lambda. And then it is a result of many people, combination of many people, Borel, Brzezinski, Joseph, maybe other people, that the associative variety of this thing is the closure of some nilpotent cone, which I denote by O lambda. And then the image of this orbit under this duality map is simply this O lambda. Okay. Okay. So in a finite story, if you start with an even orbit, even means basically means this weight is an integral weight. So its value at all the roots are even numbers. So if you divide it by 2, it's still integral. If you start with an even orbit, you get an integral lambda, and then you take W lambda to be the longest element in its stabilizer. Then you can ask what are the irreducible modules for this quotient of enveloping algebra by this primitive ideal. So so irreducible objects in the category O of G are highest weight modules, and then if you fix the central character, they're in W dot orbit of some weight. So here the weight in question is lambda minus rho. And then you show that it is annihilated by this primitive ideal if and only if it belongs to the left cell of this W lambda in the finite Weyl group. So this set is in bijection with the left cell. And right, and so here's the summary of the, so therefore, in particular, if you take the Grodiny group of this category, it identify, this is basically the left cell module. I write it in Haeckel algebra terminology. So you take the dual form of the Haeckel module associated with this left ideal and specialize Q equals to 1. And this is an isomorphism. And then so you look at this, and what do we get? So we started with an even orbit here, and you have a duality map. And so under the duality map, it corresponds to some O lambda and produce, in particular, this integral weight lambda. And so we have this quotient whose associative variety is the closure of this orbit. And then and in the finite case, there's this the Lucig's bijection we discussed before. In the finite case, it's specialized to a bijection between two-sided cells in the finite Weyl group and special orbits in a dual nilpotent cone. And since all the even orbits are special, so this corresponds to some two-sided cell for W lambda, and then you have this relation with the left cell. And on the other side, you take an element, nilpotent element here, and then, yeah, I didn't explain the, since I have some time, maybe I should explain. So you take the flag variety, which is G mod Borel, and then for nilpotent element, the affine the Springer fiber is similar as before. So you take the coset GB such that the adjoint action of G inverse of E lands in the Lie algebra of E. Okay, so this is the Springer fiber, and by Springer theory, so there's the top homology of this fiber realize a representation of W, and then you actually take some invariant by the component group. This realizes you some irreducible representation of W, and then this representation appears as a W representation. It appears in this left cell. Okay. And so in particular, you have a W equivalent surjection from this cell to this space. And what we're trying to do is an affine analog of this picture. So we started from M, an integer between 1 and h check. By the first theorem I explained, you produce some nilpotent orbit in the long length dual. This is O check M. And then I tell you how to go to this sheet. This is by writing it as a saturation of some distinguished orbit, and then apply this construction, you get some sheet. And the first conjecture says that the associative variety of this OL kappa. So my lambda before now is really, so this small lambda in the finite case is really my m lambda 0 plus rho, or maybe the dominant translate of psi m is dominant translate of this, and this is the analog of the small lambda, and okay, and then so then we basically think, well, this is some wishful thinking, but we basically want to think about this modules over the simple affine vertex algebra in the category O as modules of the enveloping algebra of the affine algebra quotient by some primitive ideal corresponding to that weight. And then so theorem 3 tells you that this orbit indeed corresponds to this two-sided cell corresponding to this element Wm. And then the conjecture quotation mark is, so you can say there's conjecture quotation mark, there's conjecture triple quotation mark. It means the level of confidence is decreasing with the number of quotation mark. But so this is something written down. This is something in the process of written down, and this is maybe further away in the process. But so the conjecture is the Grothendieck group of this K0 should correspond to the left cell module for this Wm, the way as before. And also you want to produce some affine Springer fiber. So what you do here is that you take E in this distinguished part of the nilpotent element, and then I take a generic lift of it under the Cauchy-Lucey map. This is the gamma, and so a priori you obtain an element in the loop group of the Levy, but then you can view it as an element in the looply algebra of G. And so this may not be very, very clear, but the theorem 2 is basically to justify this choice of this theorem 2 is basically it comes out of the effort of trying to understand what the element you should take to consider the affine Springer fiber. Okay. And then once you have such an element, I consider the analog of affine Springer fiber in the long-length dual Lie algebra, and I consider its top homology invariant by some component group, and then like triple quoted conjectures, there should be a surjective map like this. I think we can produce a map, but it's hard to see whether it's surjective or not. Okay, well, I think I finished, so thank you.
Okay, so it's time for questions. Anyone?
That's a good question. There should be, but it's not clear at this point. So for rational, so yeah, maybe I should say there's one case where all of this, like this thing is clear, is actually the beginning point, the starting point of this work is what is called admissible levels. So we can prove it for. So this was some joint work with Dan Xie and Min Yan. So we can show for kappa what is called the admissible level. So this is H check over some boundary admissible level, UH check equals to 1. And then in this case, the irreducible representation of the simple affine Lie algebra has been classified by Kasa and Wakimoto. And then, so let's say O of this L kappa, and we can show that this is the same as H top of an elliptic affine Springer fiber, and this is the homogeneous one. So this is the affine Springer fiber in the long length steel attached to. So this is an elliptic element of slope slope u over h check. So this is known, and then and then we want to generalize this to non-admissible levels. Means we want, well, basically you want to consider here is the maximal value n can take. So you want to consider n over u, where n and u are co-prime to each other. We only deal with u equals to 1 case in our situation, but we have some ideas and some examples for the associative varieties for general u, but it's not. It's maybe the fourth quotation mark thing, but I think a similar story should hold in that case.
So, any other questions?
So in your first theorem, you say it's OM. Is this O is special for any M? So you get this OM.
It may not be special. There are examples where I believe there is an example there's not special.
Yeah. Okay. So in theorem 2, you still go case by case in the proof? Or?
No, theorem 2 has this has a uniform proof. The idea is of this proof is well, there are some case by case argument in the middle, but the idea of this thing is that basically you try to use the, how to say, you take nilpotent element and you consider some generic lift. You try where am I? Sorry. You try to control this minimal root valuation using the cyclotomic number produced by the cyclotomic level map. So we actually can prove that for W and then shallow element, the minimal valuation is something like 1 over the value of that cyclotomic map. And this gives you a relation between that map and this reduction. And then on the other side, we need we can relate using some generalization of Karshan-Lusik's like generic lift. In the Levy case, we can compare it to some weights in the Levy, but there's some case by case computation there. But yeah, and there's also some argument.
So more questions? So if not, then let's thank our speaker again.